In our last problem, we looked at the fact that all energy in the electromagnetic spectrum moves at the same speed, which is the speed of light, such that the wavelength and frequency of that radiation are inversely proportional. So we kind of talked about interconverting wavelength and frequency. In our next problem here, we're going to actually calculate the energy of that light using a different equation. And so context of this problem is we're talking about microwave radiation. So a student uses a microwave oven to heat their meal. Wavelength of the radiation is 1.20 centimeters. What is the energy of one photon of this microwave radiation? So again, if we be consistent with this and we write down information that we know that we're using a microwave, and that microwave is going to elicit radiation that has a wavelength of 1.20 centimeters. And again, we can use a prefix conversion. So kind of getting back to how we used to think about doing problems and how we walk between information that we know and where we want to go. Well, let me just take a second here and pause and say, where do we want to go? We want to figure out the energy of one photon. Well, again, we can use a prefix conversion to get to the energy that we want, or I'm sorry, the wavelength of our species in meters. So we want to get to the wavelength in meters. And again, we can interconvert wavelength and frequency. So we can get down to frequency here by using our equation that says frequency is equal to the speed of light divided by wavelength. And then again, this equation that we just looked at here tells us that the energy is equal to Planck's constant times the frequency. So we can kind of go directly to here by saying the energy is equal to Planck's constant times the frequency. And again, this is going to give the energy for one photon. So these are going to be very small numbers, but that's okay because we're figuring out the amount of energy for one photon of this. So it's going to be fairly small. But what I wanted to point out is we can actually create a new equation, and we already wrote it on our sheet there. So we've got E equals h nu, and then we've got C equals lambda nu. But one of the things that we can do is we can substitute in, we can say that nu equals C over lambda, and put these equations together, and we can get E equals hc over lambda. So again, it can allow us to walk more directly here between our wavelength and meters. We can use E equals hc over lambda. All right, so pretty straightforward problem here. Again, just needing to make sure that things are in the right units. I'm going to use our new kind of version of this equation. Planck's constant is 6.626 times 10 to the minus 34th joules times seconds. So you'll see here how our units work out. C is the speed of light, 3 times 10 to the 8th meters per second. So again, now our seconds are going to cancel. We can see that we need to have our wavelength in units of meters so that it cancels there. So 1.20 centimeters is going to be 1.2 times 10 to the minus second meters. Meters is going to cancel. So energy, and again, this is going to be a small number, is 1.66 times 10 to the minus 23rd joules. And again, just a little note, this is okay that it's a small number. This is for one photon. So, okay to be a fairly small number.